All right, we're going to go ahead and finish up this first section that dealt with combining functions. And the last operation that we're going to talk about that is specific to functions is something called composition. All right, so what is composition of functions? Composition of functions, this is the result of plugging one function into another. To me, when I think about composition of functions, I want to think kind of like an assembly line. Is that, you have the materials, you give it to the first guy, and he does his stuff. And it turns into something else. And then as soon as he's done, he gives it to the next guy, and he does something. And gets something else. And it continues on until we get to the final product. And so that's kind of what we want to think about when we think of composition of functions. So first, let's go ahead and talk about our notation. Our notation is going to be an open circle in between the F and G. If you want, some people think of it as fog. But what it actually means is F of G of X. This is the way we read it. And what this means is we're going to take our G of X and we plug it into our F of X. When we talk about evaluating composition of functions, and that's going to be one of the first things that we start with, is we want to start on the inside and work our way outside. So for instance, if we look at something like F of G of 5, well, we take our 5 and we're going to plug it into G. And then we take that result and we plug it into F. The other thing that we're going to do is we are going to talk about simplifying a composition of functions. And just like when we evaluate composition of functions, we replace all of our variables with the number. Well, we do the same thing here, except for we are going to plug in, we're going to replace all x's with the inside function. And then we simplify the result using order of operations. The last thing that we're going to talk about is domain of composition of functions. And so when we look at this, we want to include any restrictions for g of x, or the function that we're plugging in, and any new restrictions that result. So for instance, g of x might not have any restrictions, and it would have a domain of all real numbers. But if we plug it into the denominator of another function, well, now we do have restrictions. Okay, let's go ahead and look at some examples. And we are going to start with evaluating using composition of functions. All right, so just like what we saw in the last section, we can go ahead and apply similar techniques, not only to equations, but also graphs and tables. And so, for instance, we're going to start with a graph. And the first thing I'm going to do is I'm going to go ahead and rewrite this using our other notation. And so when we rewrite this, what we're going to get is F parentheses, G parentheses, 2, and then we're going to close all of our parentheses. All right, the first thing that we want to do is we want to start by calculating or by finding G of 2. And so remember, the 2 is inside the parentheses. It is an x value. We're going to come over and look at our red graph. And if we look at our red graph, we want to find a point that has an x coordinate of 2. And that's going to be this point right here. when x is 2, y is negative 2. We're going to replace that entire g of 2 with the y coordinate. All right, so when we plug that in, we get f of negative 2. All right, so now it's just a regular function of f. We want to know what is y when x is negative 2 on our blue graph. And so we are going to look for a point that has an x-coordinate of negative 2, and it's going to be right here. And so when we find this point is negative 2, comma, negative 4. And so what we have here is f of negative 2 equals negative 4. And so what we have here is this entire thing is equal to negative 4. All right, let's go ahead and look at a couple other ones. Now, not only can we compose two different functions, we can actually plug a function into itself. And so, for instance, we're going to do that on this next one. And so we're going to start by rewriting this. I want to rewrite this as g of 0. Okay, we are going to start by figuring out what is g of 0. And when we do this, we have this point up here. It has an x-coordinate of 0, and when x is 0, y is 2. And so I am going to replace this g of 0, the inside one, with my y-coordinate. All right, this becomes g of 2. And again, we want a point on the red graph that has an x-coordinate of 2. And so this is going to be the same thing that was in the first problem, except for now this is going to be our final answer. Our x-coordinate is 2 on the red graph here, and it is equal to negative 2. And so our final answer is negative 2. All right, last one. We have g of f of 4. And so the first thing we want to do is on our f graph, on our blue graph, we want a point that has an x-coordinate of 4. And so here on my blue graph, I have the point 4, 2. We are going to keep the y-coordinate. This becomes g of 2. And again, we have g of 2 is equal to negative 2. And so same thing, and we're going to talk about composing equations in a little bit. But basically, when we talk about this g of f, is basically we're saying, okay, what's my raw materials in my assembly line, and then what's my finished product? And we don't necessarily care about all the different steps in between to get us there. That's kind of what we're talking about when we look at this composition of functions. All right, we can also do this with tables. And so if we come down and look at our tables, I'm going to go ahead and change this up a little bit. I'm going to, just because it doesn't work out, I'm going to replace my 3 with a 5. No. I'm going to replace it with a 4 for this first one. And then for the second one, I want to do f of g of 5. I did not catch this before I created the video. All right, so let's go ahead and try these. Okay, so again, we're going to go ahead and start by writing in our other notation. So I'm going to rewrite this as g of f of 4. Okay, and so the first thing we want to do is we're going to take our 4. We are going to plug it into f. And what we get is 5. And so that's going to be the entire f of 4. All right, this becomes g of 5. Okay, so now we're going to repeat the process, but we are going to plug the 5 into my g equation. And when we do that, we get 6. And so we get that this is equal to 6. And so g of f of 4 is equal to 6. All right, the next one we want to look at is we are going to go f of g of 5. And so if we do this, again, we're going to start by writing it in our other notation. All right, I am going to plug my 5 into my g equation. And when we do that, we get when x is 5, g of x equals 6. I can replace the entire g of 5 with 6. And now I want to take the 6 and plug it into my other equation. And so we're going to come over here and plug it in. And we get that this is equal to 7. And so f of g of 5 is equal to 7. All right, that finishes up working with the graphs and the tables. The next thing we're going to look at is we are going to look at equations. All right, so now let's go ahead and do the same thing with functions. The first thing we're going to do is we're going to start by evaluating. And so, for instance, on example A, we want f of g of -4. And so if we start by writing it using our other notation, what this means is I want to calculate g of -4. And so our g of x equation is absolute value of x. If we plug in -4, we get the absolute value of -4, which is equal to +4. We're going to go ahead and take this answer and we want to replace this with 4 over in our composition. And so if we do that, we get f of 4. And we're going to plug 4 into our f equation. And so what we get is 5 times 4 minus 2. And if we do this, 5 times 4 is 20. And if we subtract 2, we get 18. And so our composition is equal to 18. All right, let's go ahead and do another one. For the second one, we want g of f of 5. And so we're going to start by writing this as using parentheses. We have g of f of 5. And so the first thing I want to do is I want to plug my 5 into my f of x equation. All right, so if we do that, we get f of 5 is equal to 5 times 5 minus 2. And if we simplify, we get 25 minus 2, which is 23. Okay, we're going to go ahead and replace our f of 5 with 23 over here. And if we do this, we get g of 23, which is the absolute value of 23, which is equal to 23. And so our composition of functions is equal to 23. All right, the last thing that we're going to do is we are going to not be plugging in numbers. We're not going to be working with numbers. We're just going to be working with the expressions. And so for the first one, we want to know what is f of g of x. And so if we rewrite this using our other notation, we have f of g of x. And just like when we plug in numbers, what we want to do here is we want to replace our g of x, or our x in the f, with whatever g of x is equal to. And so if we do that, what we get is 5. I replace my x with my g of x, which is absolute value of x, and then we have minus 2. And we're done. This is our simplified function. All right, we can do the same thing going the other direction. For this one, I want to find g of f of x. And so for this one, we want to replace x in our g equation with f of x. So we're going to take our whole 5x minus 2, and we're going to plug it into our absolute value. And so what we get is the absolute value of f of x, which is 5x minus 2. And we're done. All right, the last one we're going to look at is f of x. And so for this one, again, remember we can plug a function back into the original function. We can do this with just one function. And so if we do this, this is going to be f of x. And what I want to do is I want to plug my 5x minus 2 back in for x. And so just to kind of make this a little bit easier, what we have is this is going to be 5 times f of x. We replace our x with f of x, and then we have minus 2. And here we're going to go ahead and replace f of x with the 5x minus 2. So what this simplifies down to, or when we plug this in, is we get 5 times 5x minus 2, the f of x, and then we still have our minus 2. we should go ahead and simplify this. And in order to simplify this, we're just going to go ahead and use all of our regular techniques that we use. We want to start by distributing. If we distribute, we get 25x minus 10 minus 2. And when we combine like terms, we get 25x minus 12. All right, so those are some examples. Now we're going to go ahead and look at a couple more. All right, we're going to deal with a little bit more complicated examples here. And we're just going to go ahead and find the composition of functions. And the main thing that we do want to do with these ones is we are also wanting to identify the domain. All right, so for the first one, we have f of x equals 1 over x plus 1, and we have g of x equals 5x. All right, the first thing that we want to do is we're going to go ahead and plug in. And so what I want to do is I'm going to rewrite this as f of g of x. And what this means is I am going to take my 5x, I'm going to replace it in my x, and so I'm going to replace the x in the denominator with 5x. All right, if we do this, we get 1 over, we replace our x with 5x, plus 1. This is our simplified function. We can't do anything else with it. But we do want to know our domain restrictions. Now, the first thing we're going to look at is, okay, what are the domain restrictions for g of x? And because g of x is a linear function, g of x has a domain of all real numbers. So we don't have to worry about that. Now, the second thing that we have to consider is the combined function. Does it have any restrictions? And it does. For our combined function, we have that 5x plus 1 cannot equal 0. And so if we go ahead and solve this, we can subtract 1 from both sides, and we can divide by 5. And so we get x is not equal to negative 1 over 5. You can write this in interval notation if you want, but for most of these, this is all that we're going to be looking for. All right, let's come over to the second one. We want to find g of f of x. And so for this one, what we want to do is we want to replace our x in our g equation with the function f of x. If we do this, we get 5 times 1 over x plus 1. And you can go ahead and simplify that. We can go ahead and rewrite 5 as 5 over 1. We can multiply straight across, and we get 5 over x plus 1. All right, we want our domain now. And so we are going to start with the domain of the original function, or the function that we're plugging in. F of x does have a domain restriction. We do have x plus 1 cannot equal 0. And so we have x cannot equal 1. Now this is our restriction for f of x. But we're also going to see that in our simplified function, in our combined function, we have the same domain restriction. We have x cannot equal 1. All right, let's try a couple other ones. If we come down to our next examples, we do want to find f of g of x and g of f of x. All right, for example A, we're going to start with f of g of x. This is equal to, if we get rid of the circle, this becomes f of g of x. And I want to take my g of x and plug it in for x in my f equation. And my g of x is equal to x squared plus 5. And so what we're going to get is this is equal to 2 times g of x, which is x squared plus 5. And we have minus 3. If we simplify this, we get 2x squared. We're going to distribute plus 10 minus 3. And when we combine our like terms, this becomes 2x squared plus 7. All right, now we're going to go ahead and go the other direction. And so the other direction, we're going to do g of f of x. And for this one, what we want to do is we want to take our f of x, and we're going to plug it into g. And so wherever we see our x, we are going to replace it with 2x minus 3. And so when we do this, we get 2x minus 3 squared. And then we have our plus 5. Now for the squares in the homework, I do want you to go ahead and simplify them completely. You can have cubes, you can have all sorts of other things, and those ones I'm not going to worry so much about. But for the square, these are things that we've done for many years now, or for many semesters. And so we can go ahead and simplify this. If we go ahead and simplify this, we do want to FOIL the 2x minus 3 times 2x minus 3. And if we do this, we get 4x squared for our firsts. Our outsides, we get minus 6x. Insides, we also get minus 6x. And lasts, we get plus 9. All right, if we go ahead and combine our like terms, we get 4x squared minus 12x plus 14. For both of these, because f of x has a domain of all real numbers and g of x has a domain of all real numbers, then what we're going to get is we don't have any domain restrictions for either composition. And so our domain for both, I know it didn't ask for it, but just to practice it a little bit more, for both is all real numbers or negative infinity to infinity. All right, let's look at another example. Okay, so for part B, we also want to find f of g of x and g of f of x. And so for part, let's start with f of g of x. So remember that we're going to plug in g of x to our f of x. In order to do this, we have g of x. We're going to replace all of the x's in our f of x with this expression. And so if we go ahead and do this, what this is equal to is the square root of 2 times 1 over x plus 1. And if we go ahead and simplify this, we can go ahead and multiply. We can rewrite this as 2 over 1. What this becomes is 2 over the square root of x plus 1. All right, though it didn't ask, we're going to go ahead and calculate the domain. So for our domain, if we look at the original function, we have that the domain, we cannot plug in 0, or we cannot have a denominator of 0. And so if we go ahead and solve this, we get x is not equal to -1. Now, if we look at our combined function, we have that the inside of our combined function has to be greater than or equal to 0. Now, for this, in order for this to be negative, we really only care about the denominator. And so if we set the denominator greater than or equal to 0, what we get is x is greater than or equal to -1. And so now if we go ahead and combine these two statements, we have x cannot equal -1. We have x has to be greater than or equal to -1. And so our combined domain, or our domain for f of g of x, is -1 to positive infinity. All right, let's go ahead and look at g of f of x. And so we are going to plug in f of x into g. And so when we do this, we are going to plug in f of x for x. And so wherever we see an x in our g function, we're going to go ahead and plug in the square root of 2x. All right, so when we do this, we get 1 over the square root of 2x plus 1. All right, it doesn't look very nice, but that's what it's equal to. We're going to leave it like that. All right, when we look at our domain, we want to talk about, okay, let's start with the first one. We want to talk about the domain of f of x. And so for our domain of f of x, we have that the inside thing has to be greater than or equal to 0. And when we look at this, when we solve it, we have x is greater than or equal to 0. Now for our combined function, we need to have that the denominator is not equal to 0. But if we solve this, what we get is, or if we try to solve it, what we get is the square root of 2x is not equal to -1. And that's not going to happen anyway, because we already have that we are only plugging in numbers greater than or equal to 0. And so this is never going to equal -1. And so for this, my domain is just the domain of the f of x function, the function that we're plugging in. All right, that takes care of the first two. We've got one more. All right, for example C, we have f of x equals x plus 2, g of x equals x cubed minus 2x squared minus 1. The first one is going to be really easy. Okay, we want f of g of x. And so what this means is we are going to plug in g of x wherever we see an x in our f of x function. So here, g of x, we're plugging it in right here. We are plugging it in right here. And this is what we're plugging in. And so if we do this, what we get is, this is x cubed minus 2x squared minus 1. And then we still have our plus 2. And our plus 2 is coming from our f of x. All right, if we simplify this, what this simplifies down to is x cubed minus 2x squared. And if we combine our constant terms, we get plus 1. Now, for the second one, for g of f of x, this one gets a little bit more complicated. And so when we do this, our first step is basically the same thing. So we want g of f of x. And what this means is I want to take my f of x. I'm going to replace all of my x's in g with this expression. And so what we get is x plus 2 cubed minus 2 times x plus 2 squared minus 1. And I'm going to say you can go ahead and leave it like this. But just to show you kind of what happens if we do try to simplify it. Well, if we try to simplify this, we're going to go ahead and start with x plus 2 squared. All right, this is x squared plus 4x plus 4. You can either FOIL this, or you can go ahead and use the formula for a square of a binomial. And I'm going to go ahead and plug that in for my x plus 2 squared. We have x squared plus 4x plus 4. I still have my minus 1. And now the last thing that I want is I still need to figure out what is x plus 2 cubed. And so I'm going to go ahead and multiply this by another x plus 2. And if we do an extended FOIL on this, I'm going to start by multiplying every term in my second set by x squared. And so what we get is x cubed plus 2x squared. All right, so that's this first one. All right, the next thing I want to do is I want to multiply everything in my second set by 4x. And if we do that, we get 4x squared plus 8x. And for my last one, I want to multiply everything in my second set by 4. And what we get is 4x plus 8. And so those are those ones. All right, we can go ahead and simplify this now. by combining like terms. And what we get is x cubed. We have 2x squared plus 4x squared. That is going to be 6x squared. We can combine the 8x and the 4x. That gives us 12x. And we have plus 8. All right, we're going to take this and put it back into our problem. So we have x cubed plus 6x squared plus 12x plus 8. All right, we need to go ahead and distribute. So I'm going to bring down the x plus 2 cubed, the simplified form of this. I'm going to distribute my negative, and we get minus 2x squared minus 8x minus 8 minus 1. And then if we go ahead and combine our like terms, I have a mistake right here. This should be a 6x squared. If we combine our like terms, we get x cubed. I can combine my 6x squared minus 2x squared to get me 4x squared. I can combine my 12x minus 8x, gives me plus 4x. My positive 8 and my negative 8 cancel, and we have a minus 1 at the end. And that is our simplified function. Now, if you do want to kind of do a little bit more practice with these, this is what you can do, is you can go ahead and expand it out as far as possible. All right, that finishes off these examples. We've got one more thing that we're going to go ahead and do. The last thing that we're going to do is we are going to break down a composite function. And so basically what we're going to be told is the final answer. And we want to know, okay, what did we combine in order to get this? We want to find two separate functions that when you compose them, give us the given function. If you go on into calculus, this is going to be a very important concept that you will see, and it's associated with something called the chain rule. For now, we're just going to go ahead and try to break them down. Now, one thing to note is that for some of these, there is going to be multiple ways that you can do this. And I'll show that to you on a couple of them, okay? But for instance, if we start with h of x, I want to try to see what are the basic components that we have here. And so for instance, on this one, inside the parentheses, I see a 2x plus 1. And so what we can do is we can have that be one of our functions. I'm going to say g of x is 2x plus 1. And if we're plugging g of x into f of x, well then my f of x is 4x cubed. Now, as I mentioned, this is one possibility. Another possibility that we could do is we could just say that g of x is the 2x. And if we do this, all right, what we have is that f of x is equal to 4 times x plus 1 cubed. Okay, there are a couple other ways that we could do this. We could say that g of x is equal to this whole thing, the 2x plus 1 cubed. And so if we do that, what we get is g of x is equal to 2x plus 1 cubed, and f of x is equal to 4x. So again, there's lots of ways to do this. For me personally, the one that I first see is this top one. All right, let's look at a couple other examples. All right, if we come to example B. Example B, we have h of x equals 2 over x squared minus x plus 1. I'm only going to do one of them on here. And so for me, when I look at this, the first thing I see is, let's let the denominator be one of our functions. So if we do this, we have g of x is equal to x squared minus x plus 1. And to get h of x is we are plugging it into the denominator. And so we can say that f of x is equal to 2 over x. Again, there are other options that you have for this, but this is the one that stands out to me the most. All right, let's look at one more. Let's come down to c of x. All right, same basic idea here. Is when I look at this, one of the things that I see is I have my x squared plus 1. And I am plugging that into a cube root. And so that's how I'm going to break it down. I'm going to let g of x be the inside thing. And I'm going to let f of x be the outside thing. And so my outside thing is just a cube root of x. For this one, just to show you that we can do it another way. For instance, what I can see is I'm just going to plug in x squared. And so if we let g of x equal x squared, well then f of x is the rest of the stuff. And so f of x is equal to the cube root of x plus 1. All right, that takes care of these problems. And that takes care of the section. All right, so again, in here we talked about composition of functions, and we're actually going to apply it in the next section when we talk about inverse functions. Okay, go ahead, take a break, and we will come back again and look at the next section.